Okay, let's go ahead and get started. I was told that some of you may not have got your lab notebooks. Who here does not have their lab notebook returned to them? What day of the week do you know?
Thursday.
Thursday, that's Dalen's group. Anybody else not have their lab notebook? I saw Joey back there, so I think the Tuesday, Wednesday, Thursday morning, or Thursday early ones got theirs. So Dalen's group is the only one that may be missing. He may show up in a few minutes here. If not, what I recommend you do is, if you do some work that needs to go into your notebook, just put it on some paper and then add it in, staple it in later when you get notebooks back. If you have his email email address, maybe shoot him and I'll say, hey Dale, Dr. Hunt wants to know where you are. Or I'll do that this afternoon. Okay? So I apologize for that. Let's take a look at where we are. This is the course calendar as it's shown on Canvas. We're in the yellow highlighted week number 6. The semester is going away quickly. So I look forward to progress reports at the end of this week. Today the topic is the programmable timer, and person A of the team should write their second and last memo of the semester. Okay, this is a progress memo. Just kind of summarize what you tried to get done over the last couple of weeks. And there is a case study for you to also look at. It's looking at the Volkswagen diesel emissions. I guess it was a scandal. I guess we could call it a scandal. I thought it was pretty good engineering, but remember the goal here is to take a look at the case study and then apply the tenets of the IEEE Code of Ethics and come to some conclusion about how to handle the situation. All right, so our topic today is this, programmable timers. Okay, so we're going to be using a timer now we're going to use the timer to produce interrupts. And so the basic idea is the following. Oh, by the way, the reference manual has additional details. This is in chapter 18. This is the basic idea. And so the main thread is shown there in kind of blue colored. And periodically, every t units of time, an interrupt occurs, and then we'll go up to an interrupt handler. All right, and the interrupt handler then does something. And there could be a variety of things that an interrupt handler may do. And so this slide talks a little bit about some things that could happen in a computer system that are driven by time interrupts. And this semester we'll do all 4 of these things at different times. Okay, they're coming up. You can periodically interrupt the CPU to do something. Okay, so in your term project, you're going to design a control system, and that will require a timer interrupt. Oh good, Dalen's here. This week, we're going to use the timer to provide accurate time delays. We're going to try to do a more accurate stopwatch rather than using software loops. In another week or so, we're going to take a look and use the timers to produce a periodic waveform, just repeating over and over again, produce this waveform. And in particular, it will be a pulse width modulation signal, so that's something coming up. And then the timers can also be used to measure how much time elapses between events. And we'll use that as one way to measure the speed of the motor. So all 4 of these tasks are things that we'll explore this semester. But the focus this week is this one, provide an accurate time delay. This is at kind of a high level, a sketch of what the timer module does. Okay, there's some additional details which we'll get into in a few minutes. Basically what we have here is a binary counter. Its initial value could be presettable. That's the idea of a reload. Sometimes the preset could be 0, it could be a non-zero number. We'll talk about that a little bit. And it basically produces an output that we call the current count. Now what is it that is it counting? It could be counting events that are not happening periodically. We may be counting how often these happen, like measuring the time between them. Or we could be counting and see how many times these events occur over a certain period of time. That's another way you could do it. Alternatively, we may be driven by a clock, and as the clock is running, we're counting the number of ticks. Now, this line here shows that what can happen is that periodically you can set up the timer to reload itself. So for example, maybe what you want to do is say, like this week, you say every 10th of a second I want to increment a digit. So you may want to reload a counter value which is equivalent to a 10th of a second and then count down. Or maybe you reset it to 0 and then count up to that number. But there's the idea that you can periodically reload things and just start all over. Timer modules are able to do several things. In general, they are able to interrupt. This is one thing that we're going to do this week. We're going to use this feature. It's going to interrupt the main thread, and then what we're going to do is do something. In this particular week, we're going to basically update the digits on a stopwatch. The other thing we can do is we can use the output of the timer to produce some event at an output pin, and we'll do that in a future week and produce what is known as a pulse width modulation signal. Okay, so there are a number of timers in the microcontroller that we're using. We're using the STM32L100, and it's got several programmable timers. They're listed here in this left-hand column. Some of the timers can count only up. Some of them can count up or down, depending on how you configure it. They all can produce interrupts, and some of them are able to do different things with hardware. So for example, OC means output compare. I can, when my timer overflows, when the time has elapsed, I can do something at an output. I can turn the output on or turn it off. I can also monitor a pin and measure the time between events on that input pin. Or I can see how often that input pin changes. And these are all different things that I can do with input catcher. So when it's output compare, when it's input catcher. The other thing I can do is also produce a periodic waveform. We call that a pulse width modulated waveform. So these are the basic programmable timers. They all use 16-bit counters. Now there are other timers which will not need to use this semester, but you may want to be familiar with them or be aware of them. One of them is what we'll call a watchdog timer. The watchdog timer is an idea where we say we're not maybe totally sure about our programming skills or accuracy. We don't know if there's a bug in the system. And we may be concerned that we may go off on a tangent and not come back to where we're supposed to. And one way to get around that is to use what is known as a watchdog timer. And a watchdog timer is just something that just runs on its own, and when it expires, it does a hard reset on the system. So if you've wandered off and not gotten back to what you were supposed to do, the system just does a hard reset, and we start all over. Now you may say, well, I don't want to do a hard reset. I want to just keep up with that watchdog timer, and that's what this feature is. It's counting down. And what you need to do is, if your software is running properly, it periodically goes back to the watchdog timer and basically resets it, make sure it never runs down to 0 or overflows. And so that's one way to come up with what we believe is a safeguard to correctly operating software. There's a real-time clock that's available that measures time delay in real time and can maintain a calendar. And then there's also what we just call a system tick timer, and it can be used as well. Now, in this previous diagram, I said that there are different inputs that the counter can count. It can count events or it can count clocks. And among clocks, it turns out that there are different clock options. And so I'm going to go over briefly here the 4 different clock options. When the system first boots up, we have a multi-speed internal timer, there's an internal oscillator running at just a little over 2 megahertz. Okay, so when you first boot up, this is the default clock. If you don't want to use the default clock and want to have a high resolution clock, you can use a high-speed internal clock, and it runs off the internal 60 megahertz counter. But this is something that has to be turned on with software. And so these lines here basically show how you set up that timer. Basically turn on that high-speed internal oscillator. You gotta turn it on, wait for it to get ready, and then get running. You could have an external, several external sources of clocks. There's a high-speed external clock input. It uses 2 pins on port H, port H0 and port H1. On the discovery board, it's already tied to an 8 megahertz crystal, I believe. And there's also a phase lock loop input, which is an external input. So this semester, or in this course, I've seen students primarily use this counter and this counter, because these are the two, not counter, clocks. These are the 2 clock options that are available to us easily. But if you want to use the internal one, it requires a little bit of code as shown there. Okay, so I want to now come back to this counter here and kind of dig into this a little bit. And dig into this and into this little interrupt here. So we're not going to look at the output right here. We're just going to kind of look at these 2 blocks and flesh out a little bit more of the blocks that go inside there. And so this is kind of the basic timing function. We have a clock coming in, so that would be right here. The default is the internal clock that can be changed with some programming. And the clock controller, basically, it can pass a signal or not. You have to enable it, and there's a command that has to be done in order to enable the timer system. And then basically clock ticks start coming in here. And then there is what is known as a pre-scaler. You may choose, for example, to say, I don't want to count every single clock tick. I may want to count every 10th tick or every 4th tick. This is called a pre-scaling. And so that's an option for you. And then what comes out of here is going to be some multiple of what is coming into the pre-scaler. The pre-scaler could be an option of 1 or other values. And then it runs to this counter, and the counter just starts counting that up. There is what is known as an auto reload register. This is a number where that basically kind of defines how often you want to do things. Now, there's several ways you can do this. You can set the thing up so that you count up, and what happens is when you hit the auto reload register value, then instead of counting all the way through to 16 bits, what is 16 bits? 65, 536. You could set up an auto reload register value, which is smaller than that, say 1,000 counts. Once you hit that, the counter automatically rolls back to 0 and starts all over. So it's counting 0 up to the auto reload register value, and then goes to 0 and starts all over. Alternatively, you can set up the timer to count downward. When it counts downward, what it does is it starts off with the auto reload register, it gets loaded in here, and it counts downward. -1, -2, -3. And then on to when it hits the 0, it automatically reloads that value and you start all over again. So that's what this idea is here, is that you can set up either to count up or to count down and then to reload things. What can happen then is that we can, the counter can also generate then interrupts. And that's an event, and we're going to take a look at a little bit more detail there. Okay. All right, so let's take a look at the interrupt. Okay. So again, this diagram has these 2 blocks, and in this diagram they're shown here. There's an auto reload register value, there's the actual counter, there's the pre-scaler. So these 3 green blocks are these 3 blocks right here. And what we're saying is that you can also, when the counter reaches a certain condition, like it hits the auto reload value or it rolls over to 0, it can produce a flag. It says, I'm done, I've overflowed. Okay? This name here is the register where this flag occurs. So this is the name of the flag inside the box. And this is the name of the register. That's a status register. It's a status register for timer X, and X is a number, like 10 or 9 or 11. Okay? This is the other register. It is a control register. I don't remember what the D stands for, but it's a control register. And it has another flag. It just says basically that E is an enable. I can enable whether or not the information from the flag comes out and generates an interrupt in the system. That's basically an AND gate. So if the enable is 0, then this flag value never passes out. Okay? So this is a concept that we've seen before earlier in the semester when we were looking at the interrupts in our system, when we look at, for example, interrupts due to binary inputs. And again, we have this type of structure in several places in the interrupt system. So timers also produce interrupts, but they can be enabled or disabled or blocked from appearing through this type of AND gate. Okay. The information down here basically talks again about how these prescalers work. Let's take a look at that formula for a moment. Okay. So how much time is elapsed? Okay, is 1 over the frequency of the counter, and it's related to this little equation here. So the prescaler value is this prescaler plus 1 times 1 over the frequency of the clock. The total time interval then is equal to this timer count, which is affected by the prescaler, and then you add auto reload register value plus 1. Okay? It's because our counter does not count 1, 2, 3, 4, 5, 6, 7. It counts 0, 1, 2, 3, 4, 5, 6, 7. And so 0 is always one of the values in the count sequence. And so that's why the actual number of counts is 1 more than the number that you have for the auto reload register. And the same thing is true for the prescaler. And so the overall formula is not just simply the prescaler times the auto reload value, but you have to account for these little plus 1s in there. So in your formula there. Okay. So to illustrate that, there's this diagram here. This is showing 2 different cases. The first case up here is showing us what happens when we use a prescale of 0, no prescaling. If prescale is 0, then you add a 0 right in here, and so basically the clock is just counting, the counter is counting every single clock tick. Okay. If prescale is equal to 1, then you're going to count every other clock tick. And so with a prescale of 0, I'm going to count every single clock tick, and so you see the timer clock, this signal, is the same thing as the clock that's coming into the counter system, all right? The internal clock. So we have to enable the system, and then once you enable the system, it starts counting. And it's counting 1 for 1 here, because the prescale is 0. The auto reload register has been set to 36 in this example. And so you see the actual count values. It starts off with a count value of 31, 32, 33, 34, on up to 36. Once you reach 36, that's the auto reload value, and then it rolls over to 0. And you see the count starts off at 0, but 0 takes up time. So it's 0, 1, 2, 3. So it doesn't roll from 36 to 1, it rolls from 36 to 0 and starts up again, which is why this formula is auto reload register plus 1. So you say, well, how many periods are there really when auto reload register is 36? There's actually 37 counts times the period of my timer clock. When the timer overflows, when it hits the auto reload register, a flag goes on. The counter overflows, and we generate flags here. You can the interrupt flag here goes out. Okay. The lower example shows you what happens if the prescale is set equal to 3. So if the prescale is set equal to 3, then prescale plus 1 is 4. And so what happens is every 4 ticks of my internal clock, I get 1 tick of my timer clock. And so the timer is counting every 4th internal clock tick. Again, the counter needs to be enabled in order to do its work. And then when it rolls over, again, the prescale is 36. Not the prescale, the auto reload register is 36. It goes from 36, it rolls over to 0. 4 more ticks occur, and then the count goes to 1. All right? Any questions about prescale and auto reload?
What was the clock speed again?
In this case here, the default is the internal clock, 2.097 megahertz. But it doesn't have to be 2.097. You can choose to use the high-speed internal clock, which I mentioned earlier. But that requires a little bit of a few lines of software to turn that thing on. let's talk a little about some of the registers that you'll need to be aware of. There's the actual count that's going on. It's the timer counter. It's a 16-bit counter. It can be an up counter. It can be an up or down counter depending on the type of counter you're using. Some of them can only count up, timer 6, timer 7. Some can go up or down. Okay, so you have to choose the particular type of timer you want to use. There is the pre-scale register, which I explained earlier. It says I can count every nth tick. And then there's the auto reload register. These are the registers whose values basically kind of are that enter into the calculation of how long it takes to do something. Now, to use the timer, there are several other registers. So let me go back to this diagram. This diagram shows, for example, there's some flags. There's a flag that goes on when the event occurs that I've reloaded. There's also an interrupt enable. Okay, and these are registers that control the operation of things like the interrupts. And so one register that's not shown on here is the fact that you got to turn the whole system on, and that is the timer system control register. Timer X. So if you want to use timer 10, X would be 10. Control register 1. By default, these are all zeros. And so if you want the counter to run, this bit here needs to be turned on to a 1. And this is an example of how you would do it. This is now turning on timer 4, enabling the counter in timer 4. The status register is where the interrupt flag is. Okay, so this flag will go on. It basically says, look, I've got an interrupt pending. But that doesn't mean the actual interrupt actually goes through. Remember, this is ANDed with another flag in another register called the interrupt control register, DIER. So this flag needs to be enabled, and this flag is what actually happens when the counter overflows or runs the auto reload value. It's got to be ANDed with this flag. And so if you want to enable interrupts so that you can periodically be enabled, generate an interrupt, go and do something like update the stopwatch digits, then this flag will need to be enabled in the timer interrupt control register. The clock source, as I said, there are multiple clock sources. There's the default clock source, there's a high-speed interrupt source, but the clock itself needs to be enabled. So let me go back to our previous block diagram to talk a little bit about that. I think it was, let me see if I can find it here. Here. Okay, just because you got a clock by default, that doesn't mean that clock's going to get through here. Okay? So we need to make sure that your clock, our timer clock is enabled. And so there are different options here. Okay? So the clock can be derived from the peripheral bus clock, or it could be used, you can use other clocks here. And so what you see here in blue are different options depending on which timer you want to use and which timer source you want to use. Okay. All right, the default, as I said before, when you first boot up, is that it's going to use a 2.097 megahertz clock. Okay. Reprogram it if you want a higher, use the high-speed interrupt clock. That was on one of the earlier slides. Let me see if I can find that. When we're talking about clock sources. Maybe not. Not so easy to find. It's in one of the earlier slides. Okay, so you have to make sure you enable your clock source for your timer. Okay, now we generate a timer interrupt. And so what's going to happen is, well, let's see, I want that, this picture. we generate a timer interrupt, and now we need to figure out what to do. We need to have an interrupt service handler, interrupt service routine. And so we're going to use the same type of technique that we learned before with handling interrupts from the digital I/O, except rather than reading a input pin or doing something like that, we're going to respond to this timer interrupt. And so just like the I/O, every timer interrupt also has its own vector. So we need to be aware of the interrupt vector table again. And so the interrupt, the IRQ number will determine where you are in the interrupt vector table, the priorities. Okay, so different timers have different priorities, different IRQ numbers. Okay. And so again, just like before, the NVIC, the nested vector interrupt controller, is what determines the priorities. And so we need to enable in the nested vector interrupt controller the timer interrupt for the particular timer we want to use. Here we're enabling timer 9. It's basically turning on IRQ number 25. It's this one, this pair. If you want to use the timer interrupt for timer 7, you would be using IRQ 44 over here. But you don't have to remember all these numbers. You can just use this name. As before, when you wrote your timer interrupt service routine, that service routine should be given a name. That name can either be put into the table, or, as we recommended, maybe you should just use the name that's already in the table, so there's no chance of typing in something wrong. It's really in your personal preference. If you feel like you can modify the interrupt vector table name and make sure you get the same name in your software, by all means go ahead and do that. And that's what this note here is at the bottom. Use either the name for your interrupt handler and stick it in the table, or use the name that's already in the table. Okay, so I mentioned that there are several interrupts. We've talked about those. We talked about the fact that there's an interrupt enable in this control register. We looked at a diagram for that already. And the nested vector interrupt controller needs to have its enable bit for that timer. So here we're enabling for timer 9. And of course, overall, the system's interrupts need to be enabled. So if your keypad controller is working right now, this is already taken care of. You already enabled this. But you need to enable the interrupt service routine vector by going to the nested vector interrupt controller and turning on the appropriate flag. Okay, so in the remaining slides, there's just a few examples. Okay, so here's an example of how to initialize timer 4. And so, got to turn on the clock to the timer. And so this is the command that is used. Calculate a prescale value. This is the formula that we need to be familiar with. It says that basically the time of my interrupt depends on the timer, the clock period. 1 plus the prescale value times 1 plus the auto reload register value. So you need to pick numbers for this and for this. Your choice of clock is going to affect the period of the clock. Okay. And so the program code could look something like this. Then you need to enable the interrupts in the system, the nested vector interrupt controller. And then finally, enable interrupts. Okay. And then once things are going, turn it on. Turn on the counter. Turn on the programmable counter, and it starts running. Okay, so the format for the interrupt service routine might look something like this. At the top is the name of the interrupt service routine. This is the name that is used in the vector table, kind of the default name. If you want to use a different name, you can go ahead and use a different name, but then in the vector table, you're going to have to put that name here. Right? Then within the interrupt service routine, just like you did for the digital I/O, you do what you want to do. Okay? In our case here, we want to update the display of a stopwatch. Okay? Later on in the semester, we are going to look at the sensor that tells us how fast the motor is going. And then we'll issue a command to an amplifier that's driving the motor. But this week, we won't do these two items. We'll just update a display. Okay? And then you clear the interrupt request, and then you're ready to start again. Now, when the timer overflows, unlike I/O, there is no signal bouncing. So in theory, it doesn't matter really where this clearing of the flag occurs. You don't have to wait to the end. You don't have to wait for bouncing to go away. You could clear it at the beginning if you wish. All right? So this is the goal. We want to try to do a more accurate stopwatch this week. 2 buttons. Okay? Button 0 is basically start and stop. Button 1 clears the stopwatch only when the stopwatch is stopped. And so that's the goal, is have 2 buttons, and when it's running, the other button basically is ignored. When it's stopped, I can clear the display. We want to do 2 digits, basically BCD formats for the units, the seconds, and a BCD format for the tenths. And so basically we'll have 8 LEDs lighting up, showing 0.0 to 9.9, and then just repeat. All right. So the timing must be as precise as you can get it. So it requires us to use a timer interrupt. We won't be using software loops. Okay, so that's the goal for this week. Any questions? All right, very good. Let me bring back the calendar. This is what we said. So Friday, 3 o'clock, hopefully I'll see a bunch of memos in the wooden box outside room 320. Trying to look around and see if any of the TAs are here. Is Graham? I saw Graham come in. Walk back up. Dalen came in. Did y'all get your notebooks? Okay. Well, have a good week then.